Welcome to This Explainer. We're about to embark on a seriously fascinating journey today. We are tracing a path that starts with microscopic atomic collisions and ends with the massive energy grid that powers our homes, our cities, and our entire modern world. It's a story of incredible engineering, delicate balances, and the sheer awe-inspiring power hidden right inside the fundamental building blocks of the universe.
Okay, picture a single atom. When just one specific type of atom, uranium-235, is split, it releases roughly 200 mega-electron volts of energy. Now that might just sound like a random number, but in the microscopic world, that is an explosively massive event. To put it into perspective, that tiny, microscopic reaction releases millions of times more energy than burning a piece of coal. Today, we're going to see exactly how science has figured out a way to harness that invisible explosive event and turn it into the electricity you use every single day.
To see how we get there, we'll follow this roadmap: preparing the uranium fuel, the fission chain reaction, controlling the atomic chaos, nuclear power plant types, and finally, a look inside a pressurized reactor. Let's get to it.
Section 1. Preparing the uranium fuel.
You see, you can't just dig up a rock and toss it into a reactor. Our journey actually begins deep in the earth with something called graphite. This is a naturally occurring, uranium-bearing mineral typically found in sedimentary rocks. It's basically this complex mix of uranium and thorium, and it is absolutely crucial for the very first stages of enrichment. We literally have to take this raw ore and figure out a way to coax out a higher concentration of the fissile U-235 isotope hiding inside it.
So, how do we do that? Well, after we extract the ore, we use a highly technical process called gaseous diffusion. Think of it like a giant, hyper-advanced filtration system. By passing the material through porous barriers, we leverage the specific properties of the uranium isotopes to selectively isolate the exact U-235 we need for viable fuel. It's a massive, multi-step sorting game.
Which brings us to Section 2, the fission chain reaction.
All right, now that we've got our enriched U-235 fuel ready to go, let's zoom way down to the microscopic level. This whole explosive process hinges on a single collision. We need a fast-moving, high-speed neutron to slam right into a U-235 nucleus. That direct impact creates extreme instability in the nucleus. It's the trigger for the whole shebang.
But one collision isn't enough to power a city. The goal here is achieving what physicists call critical mass. Basically, we need a specific neutron density. If we pack enough enriched U-235 together, we get enough of these high-speed collisions to trigger a self-sustaining chain reaction. Once we hit that exact sweet spot, the reaction just keeps going indefinitely, provided we don't lose control.
Here's what actually happens during that cascade. That unstable nucleus literally fractures. It splits right apart, primarily forming fragments of krypton-92 and barium-141. But here is the real magic. That split also spits out 2 to 3 brand new fission neutrons, alongside that massive 200 mega-electron volt burst of heat. Those new neutrons then fly off, hit other atoms, and boom, the chain reaction cascades.
Now, what's really interesting is looking at what gets left behind once the dust settles. We see very specific byproducts forming. We get lead-216, which is the most abundant product, along with the radioactive lead-217. But as you probably know, we also produce some serious long-term radioactive waste concerns, things like strontium-90 and barium-137. We even get thorium-90, which is kind of fascinating because it's both a potential fuel source and a waste product. Managing all these byproducts is a huge piece of the nuclear puzzle.
Moving on to Section 3, controlling the atomic chaos.
Okay, so we've unleashed this microscopic cascade. Now we have a completely different problem. How do we control it so things don't just run wild and melt down? We have to manage two concepts here. First is neutron flux. Think of that as a stream or a flood of neutrons flowing through the core. High flux means high risk of fission. Second is the neutron drift model. Neutrons bounce around randomly, and here's the kicker. As core temperatures go up, that random drift actually increases, making even more neutrons available to cause fission.
So that presents us with a pretty wild engineering challenge, right? If hotter temps mean more drift and high flux means more fission, how exactly do human operators drive this massive reactor and control this microscopic flood to achieve a safe, steady state?
Well, our source data highlights a brilliantly clever method using water temperature. If you raise the water temp, it actually decreases the mean fluoride concentration, which represents the average number of neutrons. That makes the water slower and reduces the probability of fission occurring. On the flip side, cooling the water down increases that fluoride concentration, making the water faster and ramping up the fission probability. It is an incredibly delicate balancing act of temperature regulation.
And it's not just water temperature. Operators have physical tools at their disposal too. They use moderators, like water or graphite, to actively slow down the neutrons. They also use control rods made of neutron-absorbing materials like boron or cadmium. By constantly sliding these rods in and out of the core, operators can literally soak up the excess neutrons right out of the stream. The whole game is maintaining a steady state, a stable flux that keeps the reaction safe and efficient.
Let's zoom out to Section 4, Nuclear Power Plant Types.
So we figured out how to split the atom, and we've engineered ways to control the chaos. How do we package all this intense atomic control into a giant macroscopic facility? Globally, there are three main types to consider. First up, pressurized water reactors, or PWRs. These are the most common and use a water-filled moderator. Then you have boiling water reactors, or BWRs, where the water literally boils right there in the core to make steam. Finally, we have can-do reactors. These are super unique because they use a liquid fluorescent oxide, or LFO, moderator. That LFO is so effective, it actually lets the reactor run on natural, unenriched uranium fuel. Pretty amazing, right?
And for a grand finale, Section 5, inside a pressurized reactor.
Let's actually step inside the containment building of a PWR to see how this microscopic chain reaction connects directly to the macro power grid. Deep inside the core, our enriched U-235 is undergoing fission, carefully regulated by those control rods. This intense reaction heats the water in the primary circuit loop to a blistering 300 degrees Celsius or more. But because it is under immense pressure in this specific design, that water never actually boils. Instead, that incredible heat gets transferred to a completely separate secondary circuit in the steam generator. Since this secondary water is at a lower pressure, it instantly boils. That creates massive amounts of high-pressure steam that blasts right out of the containment building and into the turbine building, violently spinning those massive high and low-pressure turbines you see there.
And this is where it all comes together for us. That spinning turbine shaft cranks a massive generator, churning out electricity. Meanwhile, the spent steam drops down into a cooling system, condenses back into water, and loops around to do it all over again. Finally, that raw electricity gets pushed through massive transformers, stepped up to 240,000 volts, and sent roaring out across the power grid, right to your home. We've journeyed from a single microscopic neutron slamming into a tiny speck of graphite-derived uranium all the way to 240,000 volts of roaring power. It's an absolute marvel of human ingenuity. But it definitely leaves us with a final thought to ponder. Knowing that the simple flick of your light switch relies entirely on maintaining a perfectly steady state of controlled atomic chaos, just how delicate is the balance required to keep our modern world illuminated?